Assalamualaikum and good day to everyone. Today you're going to learn about infrared spectroscopy, and I believe that most of you already understand the electromagnetic spectrum, which is I already explained in the previous chapters. So I hope that you can implement the same concept in this part, in this topic. Okay. Okay, so I will not explain more about the relationship between frequency and wavelength, or wavelength, the relationship between wavelength and energy. I will not explain again. So here we're going to focus on the instrument, which call infrared spectroscopy. So basically, infrared spectroscopy um, is in between visible light and microwave. Okay, so basically the energy is not too high, okay, compared to the UVs. Okay, so in the infrared region, okay, basically we will have a what we call as a molecular vibration. So this is molecular vibration. Okay, so in the next slide, you're going to learn in detail about the molecular vibration or the rotation of vibration. Okay. Okay, so now we're going to the sub-regions in infrared. Okay, so in the infrared region, we have three sub-regions: near infrared, mid infrared, and far infrared. Okay, so all of these is actually have their own range. Okay, like for the near infrared, about 12,800 until 3,000 per centimeter. So this is we refer to the wave number. Okay, this is the wave number, and I hope that you can know that the relationship between wave number is wave number equals to 1 over wavelength. Okay, so that is the relationship between wave number and wavelength. Okay, so here in this part, okay, so according to this electromagnetic spectrum, you can see that infrared is in this range. Okay, in this range. So most of the molecules that absorb the energy from infrared, okay, so they will actually have this kind of what we call as a vibration. Okay. Okay, so we go for the theory of infrared spectroscopy. So basically, infrared spectroscopy consists of the molecular vibrations in two major vibration, which are stretching, and another one is bending. Okay, so in order to understand more about the stretching and bending, so this is the two major vibration of motions, okay, of a molecule. Okay, so we can see that this is stretching. Okay, just like what when you wake up and then you stretch your body, and same goes to molecules. Okay, they also do stretching. Okay, so what I can say here, a bond can stretch. Okay, so bond is not fixed, so it will be like flexible, and it will stretch and bending. Okay, they will have this kind of motion, okay, in our in the molecule state. Okay, so that is for stretching, and for bending you can see that the like in this 3D form, you can see that when two bonds can bend, so this will bend to each other. Okay, these two molecule, okay, will bend to each other. Okay. However, what we can understand from this motion, the vibration modes of a molecule are quantized. Okay, so when we talk about quantized, it means that um, the motion is very strict, or um, or it can be explained by integer number. Okay, okay. So in this case, we can refer to the either wavelength or wave number. Okay, and so the motion can be determined. Okay, the motion either stretching and bending, we can identify uh, based on the range of the wavelength or wave number. So from this wavelength or wave number, it will have a relationship to the frequency, and after that you can explain more about the frequency. Okay, so this is just what we call as the motion. Okay, so you can see they are stretching. Okay, and this stretching is a vibration or oscillation along the line of the bond. Okay, okay, for the symmetry, it means that it is a symmetry. Okay, so the motion is at the same direction. Okay, however, for the asymmetry, which is not symmetry, um, each of the molecule, each of the atoms move in the opposite direction. Okay, now we go for the bending. Okay, so when we talk about bending, we have two kinds of motion, in plane and out of plane. Okay, so under in plane, okay, bending in plane, it can move in a mm, scissoring shape, and also in a rocking shape. Okay, so you can see, okay, this is the shape of scissor, right? Okay, when you cut a paper, and then you can see that the scissor is moving like this. Okay, so rocking, okay, just like you write on the wooden rock, so you can simply see, okay, the animation here. Okay, so for the out of plane, you can see that it is a twisting, so like twist. Okay, and this is wagging. Okay, okay, okay. Now we go for the conditions for IR spectra. Okay, so basically these molecules have a natural frequency of vibration equal to the frequency of incident radiation, basically. Okay, so we can estimate that, we can assume that all the IR energy has been absorbed to the atoms. Okay, and then atoms will have this energy, uh, sufficient energy to make it move in the vibration motion. Okay, and next, change in bond length or bond angle due to vibration, of course. Okay, so this is the condition that you must know, that when an atoms or molecules receive sufficient energy, okay, to make it move, and then it will move, okay, in a certain vibration. It will not move like chaos. Okay, so it will move in a certain direction, like the one that I explained just now, like wagging or rocking. Okay, it depends on the energy that being absorbed by the atoms. Okay, okay, so when there is a changes in the bond length and bond angle, so you must know that it also will due to the change in the dipole moment of the molecule. Okay. In this case, dipole moment is the things that um, you can determine either it is a asymmetric or symmetric molecule. Okay, so basically this part a lot being explained in the organic chemistry, and I hope that you can just use that information from that subject, and then you can understand more about this instrument IR instrumentation, sorry. Okay, and after that, the radiation energy absorbed, okay, must correspond to the energy difference of the ground and excited states. Okay, so you must follow the uh, energy equals to uh, the Planck constant times with frequency. So this is the things that shows that the energy is quantized. Okay, so we must follow this formula. Now we go for the next part. Okay, so basically when the frequency of IR light match with the frequency of a particular vibration mode, the IR light is absorbed, causing the amplitude of the particular bond strength or bond band to increase. Okay, so basically when the frequency or when the energy being absorbed by the atoms, okay, so the energy in this case, we will always refer to the frequency. Okay, so basically, when there's a vibration, we will estimate that there is an amplitude in that motion. Okay, so when the frequency is high, so we can know that the energy is also high. Okay. So here when the bond, you can see when the bond stretch further, okay, compared to this one, so the amplitude increase. Okay, so when we can see here, when the amplitude increase, it means that these atoms has absorbed, okay, sufficient energy from the infrared light. Okay. Okay, so this is different kinds of bond vibrate at different frequency. Yes, okay, because let's say if you have this molecule, for example, this is a single bond. Okay, so basically single bond will have a longer bond length compared to the double bond length. Okay, so this also can affect, okay, can affect the uh, detection of the instrument. Okay, so that's why in the IR, in the infrared spectroscopy, we can easily identify um, the the that's why in the IR spectroscopy, we can easily identify if the molecule have a single bond or double bond. This is very important. Okay, so the characteristic of this can be differentiate in the output of IR spectroscopy. Okay. Okay, so basically, when we try to understand the IR spectroscopic process, so you already understand that the IR spectroscopy is actually depends on the molecular vibration, and thus this instrument can actually differentiate uh, different kinds of functional group in the sample or in any kinds of solution that being tested. And so when we talk about different kinds of molecule in the sample, so we can say that either it's a single bond or double bond or triple bond, even triple bond, we can differentiate it. Okay, so but basically we must know that the the molecule must have the covalent bond. That is another one characteristic that's very important, so that it will absorb the energy. Okay, so it has a potential to absorb the energy from the infrared. Okay. Okay, so now we go for the next part. Uh, so by the time when molecule absorb the energy from the infrared light, okay, they will start have this kind of oscillation or vibration. Okay, so by the time you increase the energy of IR, okay, or of infrared lights, the amplitude or the motion also will be increased. Okay, so you can see that um, that this part, okay, you can see when a wave of infrared light encounters this oscillating electromagnetic field generated by the oscillating dipole of the same frequency. So here the two wave couple and IR light is absorbed. So that is the explanation when the IR light is absorbed by the molecules. Okay, so we can have the couple, the waves couple. Okay. Okay, now we go for the in the physical part of the instrumentation. Okay, so basically for the IR spectroscopy, we have the first one is radiation source, which is the source of infrared. Second one is monochromator. Okay, next is the sample cells, and the last one is a detector. Okay, so infrared spectroscopy is much easier to understand compared to other instrument. Okay, so basically the arrangement of IR spectroscopy is about same like UVV spectrophotometer. Okay, so here you can see that this is the source, the infrared source of energy, and here we have the sample. Okay, the sample that contain with the covalent bond. Okay, here is the sodium chloride plates, okay, as the holder of your sample, and after that it passing through the detection, okay, detection and give a signal, and then we can estimate the frequency in the x-axis, okay, and the percent transmittance in the y-axis. Okay, so percent transmittance, okay, is the same concept like you learn in the like you learn in the UV-based spectrometry. Okay, so in this case, you can see that when the y-axis is the percent transmittance, so the absorption peaks will be like this. Okay, it will show like this kind of shape. Okay, so this is one example of infrared spectrum. Okay. Okay, so now we go for the radiation source. Okay, so radiation source of infrared, basically we use the inert solid, which is very stable at high temperature, and so basically it will in the range of 1500 until 2000 Kelvin, and the heated material will then emit infrared radiation. Okay, so here the most popular sources are nurse glower. Okay, so this nurse glower is constructed of a rare earth oxides. Okay, so that is the material that being used, okay, to radiate the infrared. Okay, second one is globa. Globa is constructed of silicon carbide. Okay, also can emit infrared radiation. So now for the first source of infrared, nurse glower. Okay, so in this nurse glower, the rod is made up of a mixture rare earth such as zirconium, thorium, and cerium. Okay, so these oxides have negative temperature resistance and is non-conducting at room temperature. It's very important so that it will not affect the formation or the radiation of infrared that produced after the the production of this infrared rays. Okay, so next is heat is required to excite the element to emit radiation. So basically they will use a temperature around 1500 until 2000 degrees Celsius. Okay. Okay, so platinum wires are sealed to the ends and a current pass through the cylinder. So here this is the glower. Okay, so this is all the rare earth material that being used. Okay, so this is the ceramic holder and this is the chamber. Okay, so basically they will use the platinum leads. Okay, platinum leads is very stable. Okay, towards a high temperature. You see that this is like a tungsten lamp, right? But in here, they use the rare earth as a source of radiation. Okay. Okay, next is the globa. So globa is a small rod of silicon carbide. So basically, globa is the same like the way they made as a source of light is the same. Only the rod is different. Okay, so here it can be heated up to 1500 until 1700 degrees Celsius, and this is a less intense source than our nurse glower, but is more useful for wavelength longer than 15 micron meter. Okay, and these two source of IR infrared fulfill two requirements. Okay, both can constant over long periods of time and also can provide whole range of infrared regions from 2 micrometer to 15 micrometer. Okay, now we go for the monochromator. Okay, so basically like in the UV spectrometry you learn, we also use monochromator. Okay, monochromator is something that you need to choose the wavelength. Okay, so in the monochromator is actually consists of a prism or gratings, which can make the infrared lights disperse. Okay, and they use like slit, mirrors, filters. Okay, but in the infrared spectroscopy, basically the prism they use is made from the metal halide prism. Okay, like sodium chloride, potassium bromide, cesium chloride. Okay, so this prism, okay, is made from the ionic this is actually the ionic compound, sorry. So they have the ionic bond. Okay, so um just like what I explained just now, that in the infrared spectroscopy they have the sample must have the covalent bond, so that when the sample consists of covalent bond, then we can estimate the vibration of the vibration motion of different kinds of molecule. But if it's ionic compound, so it is uh, difficult to be analyzed using the IR spectroscopy, because ionic compound will not absorb any lights and any infrared lights. Okay, so that's why in this case, for the infrared spectroscopy, the monochromator they use is the prism that consists of ionic compound. Okay, like sodium chloride, potassium bromide, okay, and also cesium chloride. Okay, so basically this different prism will depends on the region of the infrared. Okay, so just like for the sodium chloride, the region of infrared is between 2.5 to 15.4 micron meter, and for the potassium bromide is for 10 to 25 micrometer, whereas for the cesium chloride is from 10 to 38 micron meter. However, there is always a limitation in instruments. Okay, so for the infrared spectroscopy, as you all know that it is a very simple of setup of instrument. Limitation in IR spectroscopy is number one is the mechanical and thermal instability. So as you all know that in the infrared spectroscopy there is no temperature control. So this is the main cause that the temperature when you use a very high temperature, so it will make that the energy will become unstable. So this is another one problem that always occurred when you run the infrared spectroscopy. And the other one is a water soluble. Okay, so basically as you know that water does consist of H2O, am I right? So in this molecule of H2O there is a H plus mixed with OH minus. Okay, so by the time you want to investigate any compounds in your sample that have the humidity, I mean in your sample there's also a water, okay, so they will easily detect the water. Okay, in this case you can see very broad peak that represent the OH minus, even though in the real sample doesn't contain any OH minus. So this is the problem that always occurred when you try to run using infrared spectroscopy. Okay. Okay, so just take note that glass prism cannot be used as a glass absorb infrared radiation. So you need to choose other compound that they are not absorb infrared radiation. Okay, so now we go for the sample cell. So for the sample cell, you must know that it must be transparent. Okay, so for example, sodium chloride, potassium bromide. Okay, and in this case, we have like the same thing like when you use the monochromator. Okay. Okay, and last one is for detector. So we have the first one is thermal detector to measure the heating effect. Okay, when you increase the temperature, what will happen to the instrument? Okay, so this that we can uh, study by using the infrared spectroscopy. Okay, so next one is the photon detectors. So for the photon detectors, rely on the interaction of infrared radiation and also the semiconductor materials. Okay, so now let's look for the two types of instrument in infrared spectroscopy. The first one is dispersive instrument. This is the basic infrared spectroscopy. And the other one is a Fourier transform infrared spectrometer, FTIR. So in the dispersive IR spectrometers, okay, we have this kind of IR source, okay, and then it will uh, passing through your sample, and then it will go into this slit, and then go to the mirror, and then go to the dispersive grating. So in here, dispersive grating, it will like work as a prism, okay, like a prism, and then it will diffract. Okay, it will diffract the lights that comes from this mirror, and then the signal, the real signal, will go to this exit slate and go to the detector. Okay, so this is the whole thing. Here is the monochromator. Okay. Okay, so now let's look for the disadvantages of dispersion infrared instrumentation. So basically, when you use the dispersion infrared instrumentation, as you all know, that it will require a lot of time, and to run one sample, you will need about more than 5 minutes per sample. So this is actually what we call as require a lot of time. If you have a lot of sample, then it will become a problem. Okay, and the other one is a limited energy throughput. Okay, so basically when you have the dispersion infrared instrumentation, so basically we will have these kinds of problem, which is the energy is dispersed. Okay, the energy from the source, it will disperse to other. It will not passing through exactly the exit slate. So this is the problem when you use the dispersion infrared. So what we can see from this case, okay, so basically the lights will not very accurate. I mean the signal that will get the source is not totally near to 100%. Okay, so this is the problem. Okay. Another one is difficult to increase the signal to noise, okay, by multiple scanning. Okay, so this is the basic signal that we will get after we run using the FTI, I mean the infrared spectrometer. Okay, so you can see that this is the range of a noise, and this is your signal. Okay, so noise is always there and it's random. So it can be positive or negative. Okay, so by the time you can see in this spectra, okay, in this spectra you can see when you run one time, so this is what you get. After 4 times of scan, okay, you can see that the signal is going smooth. Okay, and when you try to increase the number of scan, you can see that the spectrum, okay, the peak is clearly, you can see very clear the peak. Okay, so what I want to say here is that, okay, so by the time you increase the number of scan, okay, actually you try to increase the signal to noise ratio, which is good. Okay. Okay, now let's look for the Fourier transform infrared. So basically for the Fourier transform infrared uh, was developed, okay, to overcome the limitation of the dispersive infrared spectrometer. Okay, so basically the FTIR is much faster compared to the dispersive infrared spectrometer. Okay, so how how this can happen, okay, is actually because there is a one optical device called interferometer, okay, which is it can encoded, okay, encoded the infrared frequency, okay, so that the signal can be measured quickly. Okay. Okay, in the FTIR systems, okay, they being add up mechanical operation, which is to modulate the spectral information using Michelson interferometer. And the other one is a mathematical operation, which is computer processing, okay, to encode the information to produce the spectrum, okay, which is we call as decoding. And here, this is the optical diagram of a Michelson interferometer. So you can see from the light source, it will passing through the mirror and then go to this fixed mirror and movable mirror. And also we have this beam splitter. Okay, this is in the interferometer. Okay, and after that, it fix. Actually, it fix the whole light source. Okay, so the light will focus, okay, will focus and will not disperse, okay. So after it passing through these many kinds of mirror, and then it will go to the sample chamber, and then in here we can say that the infrared light is 100%, near to 100%, um, passing through the sample, okay. So after that the lights output will go to this mirror and go directly to detector. So we can estimate in a short period, and also we can determine the um, that the light source is near to 100%, is passing through the sample, okay. Okay, so you can see that this is what we call as interferogram, okay. So we can identify whether the analysis is good or not by referring to the interferogram, okay. So now we go further for the Michelson interferometer. So this is in the mechanical operation part, okay. So most interferometer employ a beam splitter, which takes the incoming infrared beam and divides it into two optical beams, okay. So one beam reflect on the flat mirror, which is a fixed mirror, okay, and the other one is on the movable mirror, okay. So this mirror can be moved, okay, but very short, in a very short distance, okay. Okay, so this is the method that has been implemented in the Michelson interferometer, okay. So because one beam travels is a fixed length and the other is constantly changing, so the signal which exit the interferometer is the result of these two beams interfering with each other. Okay, so the resulting signal is called interferogram, which is which has the unique property that every data point which makes up the signal has information about every infrared frequency which comes from the source. Okay, so when the interferometer is having problem, then it will give different kinds of interferogram. Okay. Okay, so for the mathematical operation, so basically in this part they do the decoding, okay, just to decode the information from the spectrum, okay, the frequency spectrum, okay, to make the signal to detect uh, much easier, okay. So this is the schematic illustration of FTIR system. So basically for the FTIR, this is the source, the IR source, okay, and then it will go into the interferometer, and then it will passing through the sample, okay. Before it passing through the sample, we can investigate the interferogram, either the instrument is good or not, and after that, it will give you the signal, okay, of interferogram, okay. And then this is very unique, okay, just to show that different kinds will have different interferogram. Okay, and after that, it will passing through the detector, and then it will comes out as a output. Okay, in the computer. Okay, and lastly, you will get your output as a spectrum. Okay, so now we proceed with Fourier transform infrared spectrometers. Okay, so basically FTIR had improved a lot, okay, compared to the dispersive infrared spectroscopy. FTIR increased the speed and also increased the sensitivity. Okay, so here, as we all know that in between 10 to 400 per centimeter is difficult to be accessed by conventional infrared spectrometers. Okay, but FTIR can do that. Okay, so here the function of Michelson interferometer is a basic component of the Fourier transform instruments. Okay, so in the dispersive infrared spectroscopy, they use a monochromator to select each wave number. Okay, but in the Fourier transform infrared, they use they replace the monochromator with interferometer. Okay, so for the interferometer, we can investigate either the instrument is good or not by referring to the interferogram. Okay, so here the advantages of FTIR. Okay, you can get the full spectra. Okay, in 1 second compared to the 2 until 3 minute for a dispersive instrument. Okay. Next, the instrument is attached to the computer. Thus, several spectral scans can be taken and averaged in order to improve the signal to noise ratio for the spectrum. Okay. Okay. So for the sample preparation part, okay, we for the sample preparation, we refer to three different kinds of sample. We have a solid sample, we have a liquid sample, and also gas sample. For the liquid sample, we can simply pour the liquid sample into circular cells made up of sodium chloride and potassium bromide. Okay, so liquid sample is a bit easier to be used. Okay, to scan. Okay, I mean, so here it can be determined directly. Okay, so in the infrared spectroscopy, we can determine it qualitatively and also quantitatively. Okay, so here no single solvent is transparent. Okay, in mid infrared region. In this liquid sample, water and alcohols are not favored to be used. Okay, so the reason behind this is because the things that I explained just now, because of the OH minus. For the gas sample, basically we will have the gas sample cell, okay, that made up of potassium bromide or potassium chloride, and this cell are about in 10 centimeter to 1 meter, and it can compensate for the small number of molecules in the sample. And this gas sample is suitable for can be run only for the qualitative analysis. Okay, next, for the solid sample, we have three different methods. The first one is mole method, second one is potassium bromide disc method, and the third one is the cast film method. For the first method is the mole method. So in this method, the sample powder is grind, okay, grind until it become the thick slurry. Okay, uh, you need to grind with your sample with nujol or paraffin oil. Okay, or chlorofluorocarbon loop. Okay, so after you have this thick slurry, then you will smear mole on sodium chloride disc. Okay, and then you can simply scan the infrared spectrum spectroscopy. So in this small method, this is good for qualitative but not quantitative analysis. Okay, second one is for the potassium bromide this method. So in this method, use mix a 1 part finely ground solid sample with 100 parts powder potassium bromide, and after that it will this mixture will be pressed under high pressure to form a small disc, okay, and a very thin disc, okay, about 1 centimeter in diameter and 1 to 2 millimeter thickness, okay. And after that, after it being pressed, the sample being pressed, okay, so the disc is can be scanned uh, by using the infrared spectroscopy. Okay, so for this, this is preparation as malt. Okay, preparation as malt, and this is preparation as a potassium bromide. Okay, so basically after you grind with sample with liquid paraffin, and then you just simply put in between the sodium chloride disc, and then you can simply scan. And for the preparation of potassium bromide disc, so basically after you grind and mix with the potassium bromide, and then uh, you will compress the powder, okay, at 800 kilopascal. Okay, so after that you will get the disc. Okay, so this can directly being scanned by using infrared spectroscopy. So the third method is cast film method. Okay, so basically in this method, uh, when you have polymer compounds, okay, so basically when you have a polymer compounds, you need to dissolve the sample, especially in the non-hygroscopic solvent, okay. So because if you have the hygroscopic solvent, then it will easily absorb the water molecules from air. So that's why you need to choose wisely what is the solvent that you need to use. Okay, so in this case, please choose non-hygroscopic solvent. Okay, so deposit a drop of the solution on the surface of potassium bromide or sodium chloride cell, and then let it evaporate, okay, to dry, and then it is also suitable only for qualitative analysis. So basically, for drifts, diffuse reflectance infrared, okay, for a transform spectroscopy. So in this method, we have powder samples which are ground and mixed with infrared transparent salt, which is a potassium bromide. So, so the sample size must be less than 50 microns. Okay, so if you have the larger particle size, the it will makes the scattering of energy um, be increase. Okay, and the baseline shift will occur. Okay, and after that, infrared bands will become broad. Okay, so the function of this is to ensure the deeper penetration of in situ radiation, okay, and to increase the scattering, okay, and next is to minimize the specular reflection. Okay, now we go for the ATR or attenuated total reflectance. So when you use ATR as a compartment that equipped with FTIR, so basically the sample can be any. Okay, so wide variety of types of sample can be used directly, okay, without any treatment before analysis. So here we can see that if you have a sample of solids, uh, like solids of limited solubility, films, threads, paste, adhesives, and powers. So we can detect directly. Okay, we can analyze directly by using attenuated total reflectance. So the basic concept of this attenuated total reflectance is that at a certain angle, total reflection can occur. Okay, so when it occurred, it will depth the penetration when reflected. Okay, so you can see from this this IR radiation. Okay, go here and then it go to your sample, and then it will go directly to the detector. Okay, and after that the evanescence wave can be absorbed by the sample. So here the wave that comes from the IR radiation will be absorbed, and then it will go directly to the detector. So in this case, the crystal that they use is high refractive index ATR crystal. So basically, it's made from the thallium bromoiodide, okay, and also germanium. Okay, so we go for the next part, which is the photoacoustic infrared spectroscopy. So basically, for the photoacoustic infrared, so basically we have this IR radiation passing through the window, and then it will absorb by the sample. Okay, so however in this case, when this is the sample chamber. Okay, so basically the pressure is about 1 atm, 1 atmosphere, and here you can see that when the energy being absorbed, okay, when the sample absorb the energy, infrared energy, so there will be what we call as a gas expansion zone. Okay, so here you can see that the heat is being trapped. Okay, the heat is being trapped, and then the signal will not directly being detected. Okay, at a very high percentage. Okay, so here the absorption of infrared by sample causes non-radioactive decay of excited vibration states. Okay, so the first one is the modulated beam. So here is the modulated beam, and then we go for the heat, the production of heat here. Okay, occurred, and modulated acoustic wave. So this is to give us some pressure. Okay, and also the microwave microphone detection. Okay, okay, so now let's look for the infrared microscopy. So when you have the FTIR microscopy tissue screening for biomarkers, okay, so we can easily determine, okay, the infrared absorbance, okay, or the sample dimensions in about 10 to 500 micrometer. Okay, so basically this instrument is equipped with the optical microscope. Okay, and this FTIR with small IR beam size. Okay, so this is the instrument that being set up with the infrared. Okay, so we go for the next part is the application of Fourier transform infrared. So for the chemical analysis, we can just simply match, okay, the spectra that we get to know the database, to know the what compound is that, okay, from the database. So in this case, we try to identify the unknown compound, okay, especially like in the forensic world. Okay, you can see that uh, we can easily determine, okay, from the database. Okay, so also we can monitor the chemical reaction in situ. So basically some chemical reaction um, cannot be uh, detected after the chemical reaction occurred. So we can simply use FTIR for the to monitor the chemical reaction. Okay. Okay, next is the structural ideas. So we can determine also what is the chemical group or functional group that are specific in the compounds. Either it is a carboxylic acid, or it's a alcohol, or it's a amine group. Okay, so we can simply determine a variety of functional group. Okay, in our sample by using FTIR. Okay. So next is the electronic information. So basically the electronic information, like we measure the optical conductivity, okay, for the insulator, superconductor, or metal or semiconductor. So we can simply measure it. Okay. So other than that, we can also use the band gaps. Okay, the Drude model. Okay. Okay, so for the qualitative application, we can simply determine the structure, identify the organic compounds. Okay, each molecule has a distinctive infrared absorption spectrum or fingerprint. So basically, in the IR spectrum, we can identify less than 1000 per centimeter is what we call as a fingerprint region. Okay, if more than 1000 per centimeter, okay, so we can simply determine the main functional group in our sample. Okay, so basically infrared spectroscopy can be used for many kinds of sample. Okay, gas, liquids, and solid. Okay, so just just go through this text. Okay, just read it. Okay, so next is the qualitative fingerprint. So this is what I mentioned just now. Okay, the fingerprint check for identity of raw material. Okay, so basically uh, each sample will have a fingerprint. Okay, so basically when we try to match the content of the sample, so we can simply uh, determine either the raw material is the same or not. Okay, so we can detect it, or we can assume it as a fingerprint check. Okay, and next is in the synthetic chemistry. So basically they will try to identify what is the compound that the chemical reaction occur, and then what is actually the chemical compound that they investigate. Okay, so this is uh, more towards the organic chemistry. Okay, so next is can be used to characterize sample in the solid and semi-solid states such as creams and tablet. Okay, so basically if you have the cream as your sample, so that we can simply direct scan by using infrared spectroscopy. And if you have a tablet, then you need to crush it first and then make it this, or just simply put on the ATR and then you give it some pressure, and then you can simply detect the signal of the scan by using infrared spectroscopy. And then after that, next uses fingerprint test for films, coating, and packaging plastic. So basically, they certain company which produce like film or coatings or packaging plastics. They will require this kind of instrument just to check either it is in the same compound or not. Okay. Okay, now how you can read the output of infrared spectroscopy. So the first step is you need to identify the main functional group, which is more than 1000 per centimeter. So in this range, like 1200 until 3600 per centimeter, you can simply determine the main functional group in your sample. And then the second step is you need to compare with standard or with the database that has been in the computer, okay, in the processing, and you can try to investigate in this range between 600 until 1200 per centimeter. This range is what we call as fingerprint region, and in this range it is very sensitive to a different structure, okay, because if you have different structure you will have different kind of fingerprint region, okay. The shape of the peak is different, okay, so that's why we call it as a fingerprint region. So this is the example of the output from the infrared spectroscopy. So basically the y-axis is the percent transmitted, okay, or the symbol is percent p, okay, and this is the wave number, okay, this is the wave number, okay, and here is the wavelength, okay. So you can see, okay, in this range, okay, 1300 and above, you can simply determine the main functional group in the compound, okay. And in this part, starting from 1000 and below, this is what we call as a fingerprint region. So this part is hardly to determine the functional group in each peak, but you need to know that in this region, okay, for example, this molecule, only this molecule will have this kind of fingerprint shape, okay. Okay, so the other example is like this one, okay, like this one also we have like this one with which is it's a alkane, okay, it's a butane, two methyl, 2 methyl butane. This is the structure, okay, this is the name of the structure, 2 methyl butane. So here you can see that in this range, okay, at 3000 we have a CH stretch. So this is stretch, okay. Stretch actually give you required a higher energy infrared, okay, compared to band, okay. So here is band, okay, this is the CH band. So you can simply understand that this is require a bit lower infrared energy, okay. So by the time you want to compare from the spectrum you get as an output from the infrared spectroscopy, you can simply use this table to identify uh, what possible functional group that you will get from the spectrum, okay. So in this case the frequency range is very important, okay. So if the intensity is strong it means that the possible of, like for alkene, is there, okay. So it means that the we can understand that there is a alkane there, CH single bond, okay. Okay, so for other main functional group also we can identify directly by using this table, okay. So I want to say that this table is very important, especially in the organic spectroscopy subject, okay. So okay, so that's all for today, and I hope you can understand all the points in the slide. And if you have any question, you can simply ask me directly via WhatsApp. Okay, and that's all for today. Thank you, guys.